Hi and welcome to maths class. Today we're going to look at the quotient rule. And before we start looking at the rule itself, I just want to have a look at when we use the rule, because one of the most important things is being able to decide which rule you use. So far we have two rules. We have composite functions, we're going to use the chain rule, and when we have products of functions, we're going to use the product rule. So here's my composite function. I've got f of x equals sine, with inside the sine function is x cubed plus 2x squared. So I can clearly see that the inside function is the x cubed plus 2x squared, and the outside function is sine x. This is a composite function. I'm going to use the chain rule. My next example is a product of functions. This one, I've got e to the x multiplied by cos 3x. This is clearly two functions multiplied together, so I'm going to choose to use the product rule. So when do I use quotient rule? The quotient rule is for functions which are quotients, which is another way of saying fractions. Here's an example. X squared plus 5 over 3x to the power of 5 plus 2x squared minus 1. So I clearly have one function in the numerator, a different function in the denominator. I can use the quotient rule here. Here's another example. F of x equals e to the power of x over sine of 3x plus 2. And here's a third example. G of x equals tan x over log base e of x. Now, there are also examples which look like quotient rules where you can use the product rule. And an example of that might be y equals sine x over x squared. I could use the quotient rule for this and I would get the right answer. But what I can also choose to do is rewrite this as sine x times x to the power of negative 2 and then use the product rule. Now, let's remember what the product rule is. For the product rule, I'm going to take the first function and multiply it by the derivative of the second function. Then I'm going to take the second function, multiply it by the derivative of the first function, and then add those together. It's more complex than the chain rule. However, as you will see, the product rule, which has gone missing, hang on. So the product rule looks a little bit complicated, but here's the quotient rule. Okay, it's worse. It's my least favorite of having to use because I have to be extra careful about which function is which. For example, which one am I subtracting? Because there's not an addition here. In the product rule, I've got an addition in the middle, so it doesn't matter which order I put them in. I have some familiar things. This is one function times the derivative of the other, and this is the other function times the derivative of the other. But they're subtracted, so it matters which order I put them in, and then I divide by one of the original functions squared, and I have to get it right which one is here. So let's look at it. If I start with f of x equals capital F of x equals small f of x over g of x, then what I end up with is that g of x ends up on the denominator squared, and the denominator is the one whose derivative is subtracted. The numerator is the one whose original function is subtracted. And then here I've got the denominator times the derivative of the numerator. It's kind of complicated. It's not too hard to use though. It's just the thing it's got in common with the chain rule and the product rule is all we need to do is identify f of x, identify g of x, and then put them in the right place. Here's another version of the quotient rule using dy dx. If y equals u over v, then the quotient rule says dy dx, where u and v are both functions of x, dy dx is going to be v times du dx minus u times dv dx, all divided by v squared. So again, the denominator stays as a denominator, but it gets squared. And then I have to subtract the second term, and the second term contains the numerator times the derivative of the denominator, all right? So we've got to make sure we get that right. And the best way to do that is just have it written down and consult it really carefully, because knowing this off by heart is not so easy. You'll get there, but it takes time. All right. What I'm going to show you now is where it comes from. And I've already written out my working so that I can just talk to you rather than working at the same time. So we're going to start with let's just start at the beginning, right? If f of x, and I'm defining f of x as small f of x over g of x, but now I'm going to define a new function h of x which equals 1 over g of x. And what that means is that I can rewrite capital F of x as small f of x times h of x so that I can use the product rule. All right, that's what I'm going to do. I'm going to use the product rule to find out what this equals. Now, in order to use the product rule, I'm going to need the derivative of this in terms not of h, but in terms of g. I can't use h dash. I need the original g of x. So what I've done here is I've told you what the derivative is of that, but in case you don't believe me, let's talk through it. So let's say I've defined h of x as 1 over g of x, and I want to know what the derivative is. I'm going to use the chain rule. I need to find h dash of x in terms of g or g dash of x, but not in terms of h of x. I'm going to use my dy dx notation only because it's what I've been using the whole time. This is not really necessary if you're familiar with using the f and f dash notation, but I'm going to use this because that's what I've been using the whole time. So I'm defining u as g of x, that's my denominator. Then I can, if I let y equal h of x, I can rewrite this h of x equals 1 over g of x as y equals 1 over u. And now it looks like something familiar, okay? So what I've got, y equals 1 over u. I rewrite that as u to the power of negative 1, and I can then find dy du, which is negative of u to the power of negative 2. Now, if u equals g of x, which it does because that's what I defined it as here, then I can find du dx and I can simply write it as g dash of x. And dy du is in terms of u, and u is g of x. So I've now got both dy du and du dx in terms of g of x or g dash. So when I apply the chain rule, dy dx equals dy du times du dx. This is negative u to the power of negative 2 times du dx. All right, so that is dy du times du dx just here, which makes it equal to what I found here. If I rewrite that, I've got negative, that's that negative there. This g of x to the power of negative 2, I've written as 1 over g of x all squared, and there's my times g dash of x there. So let's remember where we were up to. I've defined f of x as this quotient function, but then I've defined a new function h of x, which is 1 over g of x. So if h of x is 1 over g of x, that's the derivative of h of x in terms of g and g dash. I'm now going to use the product rule to find the derivative of my original function. So if f of x is this, then f dash is, now this is the derivative of the first function times the second function plus the first function times the derivative of the second function. That's my product rule, okay? Now I'm going to replace h of x with 1 over g because I want everything to get back into g in terms of g of x so that I can find an equation in terms of just f and g and not have to do this step every time. So f dash times 1 over g of x is this part. Here f of x stays, and I simply replace h dash of x with this expression here. Negative g dash of x over g of x all squared. Now I just do some rearranging. I'm going to multiply numerator and denominator of this fraction times g of x so that I can get common denominators. This is a denominator of g of x squared. This is a denominator of g of x. So now I've multiplied by g of x over g of x to give me g of x squared on the denominator, which leaves me with f dash of x times g of x on the numerator here, and f of x times g dash of x on the numerator here. Now they've got a common denominator, I can collect them together on my common denominator, and that is the product rule. The quotient rule. That is the quotient rule. Okay. So here's my first example. I've got differentiate y equals 3 minus x over x squared plus 4x. I'm going to use the quotient rule in order to differentiate this. So what I'm going to need in my rule is I'm going to need u and v, and I'm going to need the derivatives of u and v. So first of all, as my working, I'm going to define u and v. So u is my numerator. Let u equal 3 minus x and v equal x squared plus 4x. Now I'm going to find the derivatives of both of those. du dx is going to equal -1. dv dx is going to equal 2x plus 4. Okay. Now I'm simply going to write out my quotient rule. dy dx equals, and I'm copying it straight from here to make sure I don't make any mistakes. v times du dx minus u times dv dx all over v squared. I always go all over the original denominator squared. And now I substitute. Here's v. So I've got x squared plus 4x. du dx is here, so that's times -1. Minus u, which is 3 minus x. Always use brackets when you have an expression with more than one term. And I'm multiplying, or adding and subtracting. Multiplied by dv dx, which is here, 2x plus 4. All over v squared. There's v, x squared plus 4x. So x squared plus 4x all squared. Now, what I can see here is that this is quadratic. When I expand this, I'm also going to get some squared terms. So I can't stop here. I need to expand and simplify. So this one's going to give me -x squared minus 4x. I'll expand first before going through and multiplying everything by the negative. So 3 times 2x is going to give me 6x. 3 times 4 is plus 12. -x times 2x, -2x squared. -x times 4, -4x. Don't lose your denominator. All right, if I now simplify that second bracket, I'm going to get -x squared minus -2x is going to give me 3x squared. -4x minus 6x will give me -2x. Minus -4x, that's plus 4x, is going to give me plus 2x. And then minus 12. All over x squared plus 4x squared. I see no reason to expand that denominator. It's not going to simplify in any way. There's no point either in trying to factorize this. It's not going to help me. So I'm done. Now I'm going to do an example from my first sheet, which is e to the power of x over sine 3x plus 2. So let's differentiate that using the quotient rule. This is in f of x notation, so I'm going to use this version. But if you want to redefine this and write let y equals and then use u and v, that also works. But I'm going to use this version. So that means This is f of x and this is g of x. Well, I can't use f because that's here. So I'm just going to change that to be h of x. So I'm going to say let h of x equal e to the x, and g of x, that's my denominator, is sine of 3x plus 2. Now I need to find the derivative of those. That's easy for h of x. E to the power of x is its own derivative. G dash of x, the derivative of the sine function is the cosine function. And because I've got the 3x plus 2 here, I'm going to have a 3 cos 3x plus 2 as my derivative. Okay, now all I need to do is rewrite this rule, but being careful to replace f of x each time with what I've used here, which is h of x for my numerator. So f dash of x is going to equal, I'll move that up, there we go. G of x is going to stay the same, times, that's h dash of x, minus, that's again going to be h dash of x, times g of x will stay the same. Sorry, that's not h dash, that's just h of x, and g dash of x will stay the same. All over, g of x stays the same, g of x squared. Okay, so let's do it. G of x is sine 3x plus 2 times h dash of x is e to the power of x, minus h of x is e to the power of x, times g dash, which is 3 cos 3x plus 2, all over g of x squared, and g of x is sine 3x plus 2, there it is, so I just square it, so it's sine squared of 3x plus 2. I'm nearly done. There's not much I can do to simplify here. I do have a common factor of e to the power of x. I'm going to take it out just to neaten it up a little bit, but I don't really have to. And I'm finished. So the quotient rule looks more complicated because the rule itself is kind of messy, but the method is exactly the same. Identify numerator and denominator, or as in my other example, identify u and v, differentiate each one, write down the rule, and then just take extra care when substituting in to make sure that I've got everything in the right place. And that is the quotient rule.